This is a story about how I spent the last 2 years rebuilding the YouTube video widget from the ground up, reaching 1080p, 30 FPS, and in Python. That's right, Python, the notoriously slow language. How did I defeat Python's global interpreter lock? I'll show you. I'm a casual rhythm gamer, but there's a catch. I can't keep playing OS because I'll destroy my hands. I've already seen the "I can't play OS anymore, I permanently pinched my arm nerves" videos, and I'm definitely the target audience for carpal tunnel syndrome. After I watched MaxX, I realized I can destroy my entire body instead, saving my money makers in the process. I watched MaxX during the winter of 2021, and I thought to myself, oh cool. Number 1, neural networks for pose estimation exist, and number 2, I just need to compare 2 video streams to create a score. This shouldn't be that hard, right? Goals and constraints. Number 1, I want things to be cross-platform. If I'm gonna code something, it's gonna be cross-platform. I don't want to lock myself into Windows only because I want everybody to experience the fruits of my labor. Number 2, full control over video playing, seeking. This is because I want to target practice different sections of a song. I want to be able to specify what part to practice and just repeat that section until I'm satisfied. Currently, OS and DJ Max Respect does not support that out of the box. What I've seen was people recommending to look up YouTube videos on a completed section. To me, that seems like homework, not playing a game. That should be built in. The other recommendation is to repeat practicing from the beginning over and over, but then I keep practicing exactly the things that cause mistakes in the first place, whether it be fatigue or how I play the map. Number 3, cheap. This is cheap because I'm going to request just a webcam and a CPU. I want my program to reach the widest audience possible. Enough said. Some constraints. I'm only one dev and I haven't spent much money yet, just a lot of time, and there are only 24 hours in the day. Now why Python? Programming is already hard. Computer vision and media pipelines are no joke. As I've experienced with my React background subtraction example, my thought process is more aligned to Python than JavaScript. Python lets me focus on the computational side of things so I can get the computer vision work done fast. Compared to my experience with NPM, there is almost always a Python package to do something you want. Why not go C directly? Well, if you have $1 million you would like to give to me, so I could hire some experienced C++ programmers that know media pipelines and cross-platform solutions, then sure, I would totally do it. But I don't and have to make do with my current skill set and resources. Now, why Kivy? I settled on Kivy because it checks both my requirement for cross-platform and very easy to prototype. There are also Android and iPhone examples, with the camera for Kivy example being the most promising. Camera for Kivy uses TF Lite, which is the underlying foundation of MediaPipe. 3,000 hours later, version 1, React and OpenCV. This is not much. It's kind of like that very weird American TV show Hole in the Wall. However, looking back on it, it was just body shaming the TV show. The point was that if you could fit in the wall cutout, you would fit through. For gauging dance moves, this was insufficient. What happened if you had baggy clothes or your outline didn't fit? It was a good first try, but not something I would be okay with playing. There has to be a better way. Version 2, my first release on itch. 6 months later, I had discovered the wonders of Python and neural networks. Here I made my first prototype, but I'm still not satisfied. I don't have full control over the player, and I can't seek the video right. I really want to build in practice mode to my player. Version 3, FastCV app. 10 months later, I got sidetracked with a contract position for 4 months. So technically, let's say it's another 6 months later. This is my third rebuild, but it gives 2 things that are important to me: full seeking and pose estimation. How it works. Reminder that in this discussion, there is also a Python module called subprocess that lets you run code by creating a new process, such as running ffmpeg, another Python script, or even command prompt as a subprocess. In this discussion, subprocess is the child process created by multiprocessing. I have tried to Google the correct term, but to no success. This article says that you can run a subprocess using the multiprocessing module, so I guess I'm not alone in my terminology. Apologies for any confusion. In my last video, I showed my plan to do 30 FPS using multiprocessing. However, there are a couple of problems. Number 1 is the video provider. I'm not used to ffpipeLayer and the native C bindings. In my OpenCV testing, it was much easier to use ffmpeg directly through OpenCV. Number 2, I found it difficult to read the future using ffpipeLayer because I took the frame after it was displayed. For example, this was the old layout. Here you go from FFmpeg player to your display. Then you take a frame after it has already been displayed, then you analyze a frame. By that time, it's already too late. It's not right to analyze a frame after you display it to the user to estimate pose. What has changed? Instead, what I do is, before a display, I get a frame and analyze, I display to the user, and I can do whatever I want now. Before I display, I have a buffer period where I get the frame and analyze. This is where my multiprocessing kicks in, since even though pose estimation is slow, I can run 3 or 4 of them at the same time to effectively multiply my FPS to 30. Then, I display to the user. Because I have full control, I can display whatever I want. And since my Python GUI is cross-platform, I can make it anywhere and with easy prototyping. The cost is I lose the speed of C++, but that is the price I'm willing to pay since that requires more dev time as well. However, there are some challenges. This video should actually be delivered on March 29th, but what happened? Can you spot the difference? Well, it's slow. I spent almost exactly 3 months fixing this timing issue. My first attempt at a fix was that I wrote timer code, but I couldn't rely on pushing shared dictionary values from the main program to the subprograms since that has a delay. This added drift to video playing. The fix was that each subprocess knows the start time, and from the start time I can calculate the correct frame to display. One more problem was that I wasn't timing things right. I had 40 and 70 FPS timings on my lines of code, but FPS is not the actual amount of time spent. In my mind, I was thinking 40 FPS and 70 FPS together should be as fast as 30 FPS, but it's not. 30 FPS is 1 divided by 30, or 33 milliseconds. 40 FPS is 25 milliseconds, and 70 FPS is 14 milliseconds. Guess what? 25 milliseconds plus 14 milliseconds is 39 milliseconds, which is more than 33 milliseconds. I'm missing my target. Another thing was that I was sending and reading numpy arrays of 1080p quality, which are around 6 megabytes. It was taking 30 milliseconds just to read it. Now here's our hero, BLAS. Again, we are standing on the shoulders of giants. The trick is using BLAS to make the frames smaller in the subprocess, then decompress the frames in the main program. This is because I have more time to compress in my pipeline at any one of my subprocesses when I'm applying pose estimation than I do to decompress at the final stage, which is just showing pixels on a screen. I tried using numpy save compress, but it was too long, clocking in at 136 milliseconds per frame. Using BLAS, frame size for 1080p frames went from 6 megabytes to 3.8 megabytes. We can use another compression library, but I didn't know it at the time. But BLAS is made by the same foundation that made numpy, so that's cool, and I donated to BLAS, by the way. Just think about it. Without compression, how much data are we really processing? I'm going through 6 megabytes per frame for 30 FPS. In 1 second, we get 6 times 30, which is 180 megabytes. That's around 1.5 anime episodes or 45 songs of data in 1 second. In 1 minute, you have 180 megabytes times 60, which is 10.8 gigabytes. That's basically 4 HD movies or 1 AA Steam game download in 1 minute. TLDR, I didn't realize how crazy this task was at first, and I'm glad nobody stopped me, not even myself. Just thinking about the amount of data that the CPU has to process for this to work is pretty crazy and humbling. By the way, I got very lucky that FFmpeg and OpenCV can open the same file multiple times instead of producing a lock on that file. Now, the new strategy works. Before I display, I get a frame and analyze. I compress it, I display it, and I do whatever I want now since the timings are correct. Visualizer from logs. I also used matplotlib to visualize my logs after I did all my work. Very genius. How you would use it is to save the logs in the text file and run matplot_timeline.py. Here you can see several different processes and see their timings. Pretty neat if I ever have debugging issues again in the future. What about threading? With the magical power of hindsight, I was able to quickly cook up a threading example. Yes, threading does work. This is a single thread with media pipeline. It's a bit faster than the original video, but you can always slow down code. In fact, being too fast is a luxury. The problem is with media pipe full. It's slow. When you are slow, how do you speed up? This problem is hinting at fundamental software implementation. The big idea is that concurrency is not parallelism. Concurrency is the ability to run multiple tasks on the CPU at the same time. The idea is that concurrency is one stream, but you get to do a bunch of different things in that stream during CPU downtime. Good enough for many use cases. Parallelism, on the other hand, is establishing multiple streams and doing many things at the same time. Using multiple cores through parallelism is great when you need to process a lot of data quickly. Multiprocessing, as I've read it, has usually been treated as a last resort, some sort of in-emergency break glass situation. Another time concern with concurrency is inter-process communication. In Python, in order to share information between different processes, you must copy memory to the other process. In my example, a 6 megabyte byte stream representing an image frame copied to a dictionary in shared memory takes 30 milliseconds. To be fair, as someone that has had no other frame of reference, I think that's pretty good. The problem is that video playing demands just a little bit more speed and efficiency, which made me so convinced in pursuing this path, and why BLOS was such a huge game changer. Question: how much CPU is being used for threading? With media pipe full using threading, one thread is already 40% CPU, so you would think that 2 threads would be 80% CPU, give or take. Pause the video and write a comment what you think will happen. I made a test, which consists of a second thread that does the same thing, but it isn't being displayed. Let's see 80% CPU usage. I was wrong. Instead of using 80% CPU, it's just twice as slow with the same amount of CPU usage. That's even worse than my prediction. This is because, again, concurrency is not parallelism. Once CPUs start working, they have to divide time between sequential tasks. My GUI, thread 1, and thread 2. Before, tasks were only divided between my GUI and thread 1, which almost made it 30 FPS. However, adding the second thread forced the CPU to split time between the 2 threads, not magically find time to execute thread 2. This also proves that you really must test things because, number 1, nothing is better than seeing raw data. Number 2, you can't predict the underlying code implementation, especially when you're calling things like NumPy, OpenCV, and MediaPipe that are implemented in a lower level and you're just calling the Python bindings. I also think multiprocessing saved me from the file locking problem mentioned earlier, as when I was trying to do this using only threading, I kept getting async lock errors from OpenCV, which I had never seen before. Here's the other thing, this thought experiment is not counting on the fact that my Python GUI should be doing stuff as well, which may or may not be trivial time-wise, as it is in the case of web requests, widget updating, etc. In the end, in this retrospective, I can run 4 multiprocessing subprocesses at the same CPU usage of my threading example and use more of the CPU. Try saying that 10 times straight. You can say, just make a second thread, but the architecture was such that I wasn't willing to commit. And I saw that when I was creating some threading examples that I would contend with a major problem, which is async lock issues possibly caused by 2 threads trying to access the camera capture at the same time. Concurrency lets you maximize the use of one CPU, whereas parallelism lets you use several CPUs running at once. One big hurdle time-wise is communication between subprocesses, which can be dealt with by using compression libraries like BLOS. At the end of the day, if I have 8 cores, I'm gonna use all 8 cores. So what now? I built a bare-bones framework on GitHub called FastTV app. Upon this, I will then finish rewriting Amazing Dance Star. I'll also get my video pipeline in order. I want either weekly or bi-weekly devlogs, depending on time. Producing this mildly edited video already put me back quite a bit with writing and rewriting. My future devlogs will be more casual and grounded updates. If you'd like to see it or run it for yourself, click the link for my other quick start guide and feature list. As usual, here are the ending socials if you'd like to know more and support me. Thanks for watching, peace.